Hello everyone, welcome to today's lecture. So today we will talk about the fourth postulate of quantum mechanics, and this will be the last one. This will complete our knowledge in quantum mechanics for now, and then we will jump into real quantum computation like quantum gates and those things. All right. So the name of this topic is quantum measurement and Born rule. So by measurement I mean that you observe the system, all right, and you get some result. For example, you measure the spin of the system and you get some spin up or spin down for electrons, for example. All right. So in a classical system, it was straightforward because there was no constraint on measurement. You can measure the system and the system will remain the same. But in quantum mechanics, this is a bit weird because you already know that your system is probabilistic, as I say in one of the live discussions, that you don't know for sure whether the spin of the electron is up or down. You have to measure it, and if you measure it, you will get one of the results, either it is up or down, but you don't know it from before. All right. So this is the idea of quantum measurements when the outcome is probabilistic. So one of the key points is that quantum measurement is not a unitary process. So what I mean by that, if you remember correctly, the time evolution of a system, let's say it was in psi, and at some later time it was u of psi. So obviously if you act on this state with u inverse again, u inverse u psi, or u inverse is equal to u dagger, then you get the state back again. So it's a reversible process. For example, time evolution was a reversible process, but quantum measurement is not. So for example, I will state it more precisely in a few minutes. So for example, if your electron was in a 1 by square root of 2 up state plus 1 by square root of 2 down state, then if you measure, it will either be up, let's say you get the up state, then your new state will be just this, and you cannot recover. Once you get this, you cannot go back to this state again. All right. It's because this is not reversible in general. All right. So what I'm trying to say is that measurement in quantum mechanics is a non-unitary process, and that implies that it is not a reversible process. All right. So let's try to state it formally. So let's say that I have a basis. Let's call that B, capital B, which is a set of these vectors. So this is the basis, and this is a n-dimensional space. All right. So I can write any vector like this, sum over ai, where ai's are just complex numbers, ei. All right. So now if I do a measurement, if I do a quantum measurement, relative to the basis B, then this is called von Neumann, by the name of the mathematician von Neumann, or projective measurement. projective measurement. Okay, there is a point to notice here. That is, I say that relative to the basis beta, right? So if you think of it in this picture, you are doing, let's say this, you're writing your electron state in this spin basis of in the basis of z-axis, right? The spin in the z-axis. So this is up in z direction, down in z direction. So if you're measuring the spin in z direction, then you're actually measuring with respect to this basis. All right. So this is the idea. So if your state is in this state, then your outcomes, this is the postulate, that the possible outcomes will be any of the EJs, right? So it will collapse. Okay, I will define what a collapsing means, but you will get one of these states. So you are writing it in terms of these bases, and you will get one of them. All right. So this is the postulate, and it completes with the following statement: and the probability of getting EJ is, okay, so probability of J is equal to mod square of EJ psi this. All right. So as you have already worked out such examples, that if you write psi as something like this, then using the orthogonality property, what you'll get is the only term in psi which will survive is the term with EJ, and your basis is normalized. So the only term that will survive is this one, EJ, and you'll have AJ, where AJ is just a complex number, and we will pull it out, and this EJ. All the rest will go to 0, right? Because of the orthogonality property of the basis. Then what you get is nothing but modulus of AJ squared, because I pulled out AJ, which is a number, and EJ, inner product EJ, is just 1. All right. So what is the thing to notice here is that when you write psi in terms of, let's say, in terms of, let's say, A1 E1 plus A2 E2 and dot 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 up till AN EN, then you will collapse to any of these. Let's say you are collapsed in E2, your new state will be E2 once you measure it, and this new state will be normalized. Okay, the normalization process is trivial here because your state E was already normalized, and probability of, and this idea, your new psi will be this. Okay, let me write it in a proper notation. So your new psi after measurement is equal to E2, let's say, and the probability of getting this E2 was nothing but A2 squared. So this is the reason why we wrote down 1 by square root of 2 up plus 1 by square root of 2 down, because you can easily see that the mod square of this is nothing but half. So probability of getting the up state was half, and the probability of getting the down state was half. That's why this 1 by square root of 2, and this is the postulate of quantum mechanics, and that is why we needed complex numbers in general, because the mod square for complex number is a real number. All right, and One more thing here to understand is that the post measurement state is nothing but a projection in one of the orthogonal subspaces. What I mean by that is that a one-dimensional space is a subspace of a bigger space, right? A one-dimensional, and this can be spanned by only one vector, let's say E1. Let's call this E1, and then this one-dimensional line is spanned by E1. What do I mean by that? Any vector in this line can be written as some alpha times E1. All right, so when you are doing this projection, what it means is that you are projecting your bigger psi in one of the orthogonal directions. All right, so this is the idea. This is the idea of projective measurement, and this is also called complete projective measurement. Complete projective measurement. What does it mean? It means that you are projecting to one-dimensional orthogonal subspaces, so you cannot go further. For example, I mean, you had a two-dimensional vector, let's say E1 and E2. These are the basis vectors, and you have some psi here. So once you do the measurement, if you get E1, it will be projected in this direction, right? And it will be normalized. It will be normalized after measurement. What it means is that if your E was not normalized, then it will be normalized by dividing by the norm. I will work out an example in the next video, but it will be projected to one of the one-dimensional orthogonal subspaces. So you're projecting psi to E1, and once you have projected down to a one-dimensional subspace, you cannot project it down more. So that is why it's called complete. So you have done a complete measurement on the system. All right, but it can also be done in you can also do incomplete projective measurements, which I'll talk about in the next video. So whenever you see so the moral of the story is, whenever you see a vector like this, no matter what it is, and no matter how many terms are there, you can say that if I do a measurement, the probability of getting state E2 is modulus of A2 square. Probability of getting E1 is modulus of A1 square. And once you get that, your state will be collapsed to E1, and once you get E2, your new state will be E2, and you cannot recover back to psi. So this is the idea of this is Born's rule, and this is one of the most important postulates of quantum mechanics, and this is where it distinguishes from classical mechanics, that your system is probabilistic. So we will work out more examples, and I hope it will be clear to you soon. So thank you so much.